Okay, again in this problem we're going to be finding the enthalpy of a reaction, the delta H of the reaction, by using the delta H of formations of the products and reactants. So this particular problem is for the reaction between sodium bicarbonate, which we commonly refer to as baking soda, and acetic acid, which we also commonly refer to as vinegar. So we're looking at the reaction between baking soda and vinegar, and hopefully everybody realizes what that does, right? The reaction of baking soda and vinegar is how we make volcanoes. It's a nice visual reaction. So the reason we can make a volcano out of this is because it produces carbon dioxide gas. It also makes sodium acetate and water. All right, in this problem we can find the delta H's formation for everything that's involved, but we can also simplify it by determining the net ionic equation first. So that way we don't have to include the delta H's of formations for the spectator ions, because they're not doing anything anyway, so they're not actually involved in the enthalpy of the reaction. So let's first make the net or the total ionic equation and then the net ionic equation. The total ionic equation will be sodium ion aqueous plus bicarbonate ion aqueous plus acetate ion aqueous and hydrogen ion aqueous. Sorry about that. So all of these are aqueous and they break up into ions on the reactant side. On the product side, sodium acetate breaks into its ions. So again, we have the sodium ion and the acetate ion. And then water is a liquid. It's not an aqueous ionic compound, so it cannot break up. And carbon dioxide is a gas, so it does not break up. It stays together. All right, so our spectator ions then are the sodium ion, they're on both sides, and the acetate ion, which is on both sides. That leaves our net, that's our total ionic equation. So our net ionic equation is the carbonate ion reacting with H plus ion to make water and carbon dioxide. All right, so now you can go to the back of your textbook and look up all the necessary delta H's of formation. For bicarbonate ion, it's negative 692. For H plus aqueous, it's actually 0. Sorry about that, 0. Water, liquid, make sure you get it in its liquid form, is negative 285.8. And carbon dioxide is negative 393.5. And these are all in kilojoules per mole. Okay, so now we're going to sum up the delta H's of the products and subtract that from the sum of the delta H of the reactant. So the delta H of the reaction is equal to the sum of the products. So that's water, negative 285.8 kilojoules per mole, and there's only one water. And then carbon dioxide, negative 393.5 kilojoules per mole. And there's only one carbon dioxide. All of that will be minus the reactants. And you wouldn't normally need to write this all out, but I'm going to just for the sake of showing you how it would all piece together. So that reactants would be the bicarbonate ion, which there's one of. So negative 692 kilojoules per mole times 1. And the hydrogen ion, H+, which has 0 kilojoules per mole times 1. All right, so obviously we don't have to necessarily write out those times 1 or the 0 times 1, but I just wanted to show you that indeed every reactant and product is accounted for, and if there had been more than one, then we would have needed to include it. All right, when we simplify this to solve it, the product side works out to be negative 679.3 kilojoules per mole, and the reactant side works out to be negative 692 kilojoules per mole. This gives us a final answer of 12.7 kilojoules per mole as the delta H of the reaction. I'd like to point out that this value is positive. What does that mean? That means that it is an endothermic reaction. In order for this reaction to take place, it needs to gain energy. Energy needs to enter the system, and that makes it an endothermic reaction. It's going to take that energy from the surroundings. So this particular process would feel cold to us. And we actually have some experience with this. This is basically the same reaction that was inside of our Valentine's Day balloons that inflated. Instead of vinegar, it was citric acid. But it doesn't matter in this case because the counter ion to the acid, the acetic acid, was just a spectator ion anyway. All that really mattered was the H+ that reacted. So citric acid would be a different source of this H+, and it reacted with baking soda. And hopefully you remember, because I asked you to kind of pay attention to it, that those balloons felt cold as they were inflating, and that's because of the endothermic process taking place.